Exercise number 8 from the textbook asks us to do a few things with a function here. Let's just take these part by part as they come. Part A, we are asked to find the gradient of the function f of x and y equals x squared e to the y. So let's work that out. We are asked to find the gradient of f. That's written as del f, or you could write out grad f. And we want that at x and y. Now, I often use angle bracket notation because it's a little bit more compact, but here in a later part, we have I and j. So I'll go ahead and use the I and j for now. Writing the gradient in that form with the I and j, we would have the first component would be the partial derivative of f with respect to x. That'll be times I. And the second component of the gradient is the partial derivative of f with respect to y. Or to be clear, it's not specifically x and y. The first component of the gradient is the partial with respect to the first variable, whatever that may happen to be. The second component of the gradient is the partial with respect to the second variable, whatever that may happen to be. Don't want a period there, we're not done. This is just an expression for our gradient in general. Now let's look at this particular function. We have this x squared e to the y, so the partial by x looks like we will have 2x e to the y times I, plus, now we'll take the partial by y, and we get x squared e to the y j. And that is the answer to part A. That's all the gradient is. It's just a vector that we build out of a scalar valued function. This is a real valued function of two variables. The gradient is simply a vector whose components are the corresponding partial derivatives of the function in question. All right. Now part B asks us to evaluate the gradient at the point p 3, 0. So this gradient vector that we have here is a function of x and y. You can see that the way it's written also. Grad f is, or grad f of x and y is equal to this. So we can now evaluate that at any particular point we choose as long as it's in the domain. Here we have 3, 0. So the words given in part B, evaluate the gradient at the point p 3, 0, can be expressed as simply this right here. This is the gradient of f at 3, 0. We plug those in and evaluate. Plugging in 3 for x and 0 for y, e to the 0 is 1, so we have 3 times 2 gives us 6i. And again, e to the 0 is 1, we have 3 squared is 9, so we have 9j. And there is the gradient at the point P. Now part C asks us to find the rate of change of f at P in the direction of the vector u, given as stated there. So we're looking for a rate of change of a function at a point. That is, a bit of mathematical jargon that should clue you into the fact that we're looking for a derivative, right? You've been looking at these since Calc 1. Rate of change of a function at a point, we want a derivative. We want the derivative in the direction of this particular vector. So we're looking for a directional derivative. A directional derivative is easy to compute if we know the gradient, and we have a unit vector for the direction. So first, we need to check that vector to see if it is a unit vector, and if not, to make it one. So let's look at the magnitude of u. That would be 1/5 times the square root of 3 squared plus 4 squared. And the square root of 3 squared plus 4 squared, you might recognize, if you think in terms of Pythagorean triples, we get a 3, 4, 5. Or you can square that out. 9 plus 16 is 25, its square root is 5, and we have 1. So we find that the vector given to us, u, is actually a unit vector. So we can compute the directional derivative in the direction of u of the function f. We just want this at the point in question. That was 3, 0. And the directional derivative, if you recall the equation stated a few times throughout this throughout this section. There are a few ways of doing this, but the easiest one, I think, to keep track of is that it is simply the gradient of f dotted with u. We're basically taking the gradient vector and finding its component in the direction of u, or its scalar projection onto u. Now the gradient of f we found here, that is 6i plus 9j. We need to dot that with the vector u, which is 1/5 times 3i, was it minus 4j? Let me check. 3i minus 4j, yes. So there we go, we just have the dot product of these two vectors. That is 1/5 times 6 times 3 is 18. 9 times negative 4 is negative 36. 18 minus 36 gives us negative 18, so we have negative 18/5. And there we go. That is the rate of change of the function f in the direction of u at the point 3, 0. The directional derivative gives us that value. And that's basically it. This problem was broken down into 3 individual steps, but that was really just sort of walking us through what they could have simply asked the last part, right? They could have said, okay, given the function f of x and y equals x squared e to the y, find the rate of change of that function at 3, 0 in the direction of this vector. And we would have had to do all of these same things, right? Again, the easiest way usually to think of the directional derivative is gradient of f dotted with u. So we would have to find the gradient of f, evaluate it at the point in question, confirm that u is a unit vector, and then evaluate the dot product. They just broke it down into steps to kind of help guide you through this. But that's basically all there is to this problem. They didn't ask us anything to this effect, but it might be worth noting that I will point out, remember, if you have read this in the section, if not, pay attention to it when you get there. But the gradient vector gives you the direction of maximum rate of change. If you want the maximum rate of change, if you want to increase the function as quickly as possible, you would want to go from this point 3, 0, you would want to move in the direction of the vector 6, 9. And the value of that maximum rate of change is going to be the magnitude of the gradient. So that looks like, let's factor a 3 out of that. So 2 squared plus 3 squared. 4 and 9 is 13. So if we were asked at the point 3, 0, what is the maximum rate of change of the given function, that maximum rate of change would be 3 radical 13. And it happens in the direction 6, 9. So the gradient basically in a single vector tells us, basically in that single vector, it tells us the rate of change of the function in any direction we want to know, right? It tells us the direction of most rapid increase. Its magnitude tells us what that rate of increase is. And then by simply dotting it with any unit vector we choose, we can, the result will be the rate of change in the direction of that unit vector. So all of that is embodied in this single vector of the gradient of the function. So this is a very powerful tool. It's a little abstract. It might be a little weird to get used to. We have this del here can be thought of as kind of a differential operator, but it's a differential operator that acts on a scalar function and produces a vector function as a result. It's a little bit strange maybe, but once you get used to that, there's a whole lot that we can do with these. We'll be using this for a few things in this chapter, and then we'll come back and see more applications of it in chapter 16.